problem and I lost access to it. Unfortunately, this forces me to keep advertising Cplex, which is maybe not my favorite thing to do. But anyway, so be it. That problem solves in a fraction of a second. So this thing that was Cplex 4.0 was impossible is now all of a sudden with Cplex 11 in current versions of any of the good solvers, frankly, Express, Cplex, Gurobi, trivial. So this raises an interesting question. If you're interested in this application, and maybe it's occurred to some of you, it is, what if I actually went back to the original model? I took this original model, which appeared to be impossible, and we applied a heuristic. And we fixed some variables to decompose it so that we could solve it. But that decomposed thing is now trivial. Why don't we go back and try the original model? And in fact, what you find is that the original model, which appeared to be impossible, is now solvable in an hour. Probably today, more like 30 minutes. Using defaults, no tuning with the solver. And, interestingly enough, this heuristic that people were using was costing 20% in the objective function. The solution that you got by solving the actual global model, if you will, was 20% better, significantly better. So this to me is a very typical example of the kind of progression that's occurred. That problems that appeared to be impossible just a few years ago are now very much solvable. Right? And I hear this, by the way. I interviewed a bunch of consultants a few years ago, like 2 to 3 years ago, and I asked each of them, it was about 10 or 15 different consultants working in the OR area, and I asked every one of them, in your consulting jobs, does technology get in the way? Is it preventing you from developing successful solutions? And in every case, they said no. There are lots of things that can cause projects to fail, but their claim, they said, and I found it a little bit hard to believe, but they all claimed this, was that the technology and the ability to solve the models was simply not the roadblock for them. Yet the roadblocks were elsewhere. So, what led to all of this? Why was there all this change? What happened in the mathematics of these problems? Here's my explanation for what happened. I've got another history slide here. This looks at the period of time from 1950 to 1998. And the choice of these dates is not an accident, as you will see. In particular, this 1998. My claim is that 1998 actually corresponds to an extremely important time for mixed integer programming, where there was an actual qualitative change in terms of what codes could actually do. The subject in that 1 year actually changed enormously. So here's this bit of history. Integer programming, in the view of many people, really got its start in 1954. And again, you see this name of Danzig, who tremendously influenced really everything we do in optimization. We wrote a paper together with Ray Fulkerson, who many of you may know is one of the fathers of network optimization, and Selmer Johnson, where they solved the 42-city traveling salesman problem. They literally did it by hand to a provable optimal solution. It's really a remarkable paper. It's still well worth reading today, and it contains most of the outline of the basic algorithms that we use today for solving integer programming problems. It's really a remarkable paper. Into the mid-50s and late 50s, early 60s, then you see the work of Ralph Gomery, which of course was extremely important theoretical work. 1960, the actual idea of branch and bound was introduced. Simple idea, but somebody had to introduce it. And then from a practical point of view, some very important things happened around 1970. I really mentioned this already. Namely, some real practical, real-world codes became available so that for the first time, around 1970, people could start to solve real-world integer programming problems of limited size. And then an interesting phenomenon occurred. There was a period of almost 30 years of research in combinatorial optimization. I like to call this the golden age of combinatorial optimization. People like Jack Edmonds, Manfred Padberg, Fattal, Balash, Martin Grutschel, Lawrence Woolsey were developing an enormous number of powerful techniques that could obviously be applied to solve real-world integer programs. But the interesting thing is, up to 1998, none of the commercial codes were using essentially any of that theory. They were still using codes that went back to the early 1970s. They'd gotten faster because computers had gotten faster and linear programming had gotten faster, but the basic integer programming technology was the same. And what happened in 1998 is that people realized this. At Cplex we realized it. We literally went back through the literature and one by one took these ideas and built them into the codes. And this really led to a fundamental change in what people could solve. So a new generation of MIP codes got developed. I won't spend a lot of time on this slide, but this is sort of a listing of some of the key things that got added into codes right around that period of time, about 10 years ago. Probably the most important, in fact, undoubtedly the most important, was the addition of cutting planes. And this is sort of a different subject that I won't talk about today, but the most important of those cutting planes actually turned out to be Gomery mixed integer cuts, which people had discarded at some point as practically not very useful, but they actually turn out to be the single most powerful class of cuts that we use today to solve integer programming problems. So, I gave you a slide where I showed you how much faster things had gotten for linear programming. I want to give you a similar set of numbers for integer programming. So I've got two slides on that, and then I will get to in the remaining time, to talking about some case studies. There's a lot of numbers that will appear on this slide, and these numbers are based on a lot of computations over a long period of time. So it's a summary of a lot of information. I've written C here for corresponding to Cplex and G corresponding to Gurobi, and you'll see how that plays a role in the numbers that I'm going to put in front of you. Here's half of the numbers. So what do these numbers tell you? 1991 was when the first version of Cplex was introduced that actually had mixed integer programming. So when this company started in 1998, it only had linear programming. If you then go to 1992, Cplex 2.1 was introduced, and we did a measurement, and we measured that version was about 3.1 times faster. 3.1 times faster than the first version. Tested over a bunch of practical problems. Now, let me say a word about what this 3.1 means, because, well, while I would very much, I seem to have a problem here. While I would very much like you to go away with the understanding that we've made tremendous progress here, I don't want to exaggerate. So, if you buy a machine, and then you buy a new machine, and you measure that new machine is 2 times faster than the old one, then it's probably going to be true that for virtually everything you run on the new machine, it's 2 times faster. It's just more or less 2 times faster all the time. This number means something completely different. It's an average. But in fact, if you test 1,000 problems, you'll find probably that some of them are 10,000 times faster, some of them 100 times faster, and usually, typically what we found was about 20% of the problems actually had gotten slower. That's unavoidable. If you make integer programming is sufficiently unpredictable, whenever you make progress, there are always a few problems that get a little bit worse. So you need to understand what this factor means, this 3.1. On the left-hand side here, you see two numbers, sets of numbers that I have in red. In 1994, there was a big jump, a factor of 5.5, and that was due to progress in linear programming. We really had discovered how to properly implement the dual simplex algorithm. It had really emerged as a very powerful technique. And then you see this phenomenon that I just got done talking about, of taking advantage of the theoretical backlog in 1998, 1999, when in a one-year period, on average, the codes got about 10 times faster. That's a remarkable improvement in a single year. And this was a scientifically fairly carefully calculated number. So really, subjectively, the subject changed in that year. And this trend has continued up through 2008 with CPLEX 11. This had a factor of 2.5 over the previous version, but this is a 3-year period now. So not all of these time ranges are a single year. Gurobi 1.0 was about equal to CPLEX 11. Gurobi 2 was about 1.7 faster than Gurobi 1, etc., up to the present. So I don't know if these numbers, if these factors look big to you or not, but if you just think about Moore's law says that the density of transistors would double every 1.5 years, which for many years meant, roughly speaking, that the speed of computers doubled every 1.5 years. So in 5 years, that's about a factor of 10, which we achieved here in a single year in mixed integer programming. These factors add up. And in fact, they add up to these. I'll put these numbers on them. You're not going to believe them. But it's true. The subject literally bears no relation to even what it looked like 5 to 10 years ago. The factor of improvement in the algorithms over this period of time from 1991 to 2011 comes out to over 100,000. Remember, for linear programming, it was 3,000. For integer programming, it's really a phenomenal number that just bears no relation what you can solve now to what you could solve a few years ago. The machine sped up by a factor of about 1,500. That's together a factor of almost 200 million. So that converts 6 years into a second. And it really is true. We have problems today that appeared literally, if we sat down, I could show you examples of problems that appeared to be impossible 3 to 4 years ago, which we now solve in less than a second. Right? There are certainly integer programming problems that we can't solve, but many real-world integer programming problems can be solved with out-of-the-box solvers. Okay, so I want to use the few minutes that I have remaining to talk about some case studies. I've got 3 case studies, and they will illustrate sort of a spectrum of kinds of applications, the third of which is a logistics application. The first one is from the electrical power industry, which is probably the single most prevalent area of applications that we see as a company today. This is a very big application area for optimization in general, electrical power distribution. And then I have one more example that's really quite different in character. Has to do with staff scheduling. So here's my first example. Under the label of unit commitment and power dispatch. So this is a case, these are slides, by the way. This initial set of slides I have were given to me by the Midwest ISO people. They won an award recently. They won the 2011 Franz Edelman Prize for practical applications of operations research. Not optimization, just operations research. How many of you have heard of the Edelman Prize? Raise your hands. Excellent. Many of you have. Great. It's the single, you could argue, the single most important prize that the Inform Society in the US gives out. It's certainly the most important prize for applications of operations research. Excuse me, I need to take a break. I need to get some Kleenex. So, thank you. Thank you for your patience. So these are the slides that they actually gave me to use from the presentation that was part of their presentation to win this prize. Okay? What is the Midwest ISO? It's an entity that was created in the US in 2005. It's an entity that manages all of the electrical power plants in this green region of the US. roughly 1/5 of all the power generation in the US. A total of somewhere between 1,500 and 2,000 separate power plants. Before the creation of the Midwest ISO, these were really completely independent power plants that were supplying power within their local region. Right? To complicate matters further, not only were they managing this many power plants, but they also had to oversee a 57,000 miles of interconnecting transmission lines among all of these power generation units in that area. And you can imagine, when these power plants were all operating independently, there was a potential for tremendous inefficiencies. What we sometimes call the silo effect, where individual power plants behaving in a very local manner. So that's depicted by this picture here, where you can imagine 3 local operating companies with power plants. This dollar sign is an indication of the efficiency of that power plant. Some of them are new, some of them are old. This is an inefficient power plant. It's very expensive to produce power. This is a very efficient one. When they're all operating independently, you get this bad situation in which each of them probably has about the same level of utilization. When in fact, clearly it would be better to be making better use of this more efficient plant. So those are the kinds of issues that can be addressed when these are viewed as a whole. That was one of the primary reasons for creating something called the Midwest ISO. There are 2 fundamental problems that the ISO needs to solve on a regular basis. The first is what's called the commitment or unit commitment problem. And in this problem, what they do is, it's called the day before problem. What they do is they must decide for each power plant of these 1,500 to 2,000 of them, which will be in use the next day and which not. So which will be committed and which not. That's the commitment or unit commitment problem. That's solved daily. Then on the day of operations, they have what's called the dispatch or power dispatch problem. There are really 2 things that they do with this power dispatch problem. It's a problem that needs to be solved roughly every 5 minutes. That's traditionally what they do throughout the day. And this tells you not which plants to use, but in a given case, if somebody has demand for power, where does it actually come from? Where does that power come from? And how much does it cost? What are the spot prices? Right? So these are the 2 fundamental problems that they have to solve. And here's the fundamental problem that the management of the Midwest ISO had to face. So they're managing 1/5 of the power inside of the United States. They realize they have some serious problems to manage this whole thing, and they need to make some decisions about how they're going to do that. And what they did is they made a sort of a potentially risky decision. They decided to invest in using optimization as a key tool in managing that entire region. So that's a big decision for them to make. We're talking about the managers of this entity, not the OR specialists. For the OR specialists, this is easy. That's what they all want to do. But for the managers to decide, they have to somehow collect the information and make a big decision based upon what they did. And they did make that decision. And that decision involved invoking certain technologies to solve these problems. In one case, it was relatively easy to decide what to do. The dispatch problem, which would seem on the surface to be the harder of the 2 problems, has to be solved every 5 minutes. That actually turns out to be a linear programming problem. It's relatively easy to solve. We have robust methods, as we talked about, for doing that. So that was easy. The primal solution to the linear programming tells you where the power comes from. And as you might guess, if you know linear programming theory, the dual solution tells you the spot prices. All right? So as usual, the dual is quite important. So what about the commitment part of the problem? Which plants are going to be turned off and on? That's clearly an integer kind of a decision. You don't turn the plant, you decide you're going to use it the next day or not use it. Right? The traditional method for solving these problems is called Lagrangian relaxation. had been used for many years. It was a method they could use to handle these binary variables and determine when a plant should be, on which days a plant should be on and off. The problem is that Lagrangian relaxation was just an unacceptable technology for a problem of this magnitude. It was just too difficult. The method was too slow. So a new algorithm was necessary for this commitment problem. And here you see, this is from their slides. These are not my slides. Advances made since 1999. That's exactly that year, 1998, 1999, when the subject changed. And the OR people here were aware of these changes and recommended the use of mixed integer programming. This was a tough recommendation, because if you look back in the literature in the power industry, in the late 1980s, integer programming was investigated and found to be a complete failure to actually solve these real world problems. So there was a lot of resistance to using it. But they made that decision, and the decision turned out to work for them. Here you see again, these are their slides. This is just a pictorial representation of the fact that with this new system, because they're looking at the problem globally, they could be smart enough to take this efficient plant, up its utilization to 90%, and reduce the utilization of this inefficient plant down to 10%. Now you may ask the question, this is a local operator. That local operator is a plant that's not being used nearly as much. How do you convince them to do that? They must be losing money. The answer is, the system allows them to purchase at a lower cost their power from this producer. They can then sell it locally, and their profitability actually goes up because they're getting their power from a more efficient source. So this is the bottom line. This is, I believe, the final slide. This is the bottom line for why they won this prize, this Edelman Prize. Part of it was because they made a very difficult management decision, and the other was because this represented substantial, verifiable savings on the order of between $2 and $3 billion because of the use of optimization to manage this part of the U.S. energy distribution system. Well, it's a big success story. Let me go on to my next one, and I'm not sure I'll get to my third one. So the second one is quite different. The first one was large scale and involved return on investment involving significant amount of money. The second one is much smaller in scale and actually doesn't involve dollar savings. The motivation is quite different. So this is call center management example. This is an application that was worked on within the last couple of years. The company, which I'm not at liberty to name, is an internet-based company selling an online service in the US. It's one of the most well-known internet companies in the US. And the nature of their business is that they sell their service with monthly subscriptions. The customers have no investment. They don't have to buy hardware. There's nothing that locks them into using this provider. So this means if the provider doesn't provide good service, the customers will just switch. This translates into service being absolutely critical to their business models. Right? Revenues and customer loyalty are completely dependent on providing the best possible support. That support is provided through a call center. And that call center has 500 employees in this particular case. They all work in a single large room. All 500 don't work at once. They work in shifts, 24 hours a day, 7 days a week. There are 400 places to sit in this room. Literally 400 places to sit. The teams are partitioned up into teams of 30 to 40 people, each with a manager. And during a given week, you have to schedule between 2,000 and 2,500 shifts. Okay? So the problem is, given the start and stop times for each employee on each day, determine the weekly seating plan. Seems relatively easy, but you've got only so many places for people to sit, and the total number of employees far exceeds the number of places to sit. People are coming in and going out. There's no way, it's impossible to give any one person a fixed seat to sit in. The seats have to move around. And that's the source of the difficulty. Given that the seats are moving around, what's the best way that you can assign them? The issue of when people come to work and when they leave, that gets settled by a separate process that's governed by union rules and bidding process and so forth. That's given information. We just have to decide where people are going to sit down. Seems like a simple problem. The objective, each is, and this gets to the heart of the matter, each team should be seated as close to each other as possible. So you have these teams. Clearly, this team is not going to be able to work as a team if 3 people are sitting here and 5 others are sitting way across the room at another place. So the key constraint is just that they need to sit next to each other. Adjacency is required in order to function as a team. Seating plan should change as little as possible from one week to the next week. And note, the objective here is not economic at all. It has to do with how well this thing functions, and it also has to do with how happy the employees are, because the seating plan affects that as well. So the constraints, here's just a quick list of some of the constraints. Seating plan must be consistent with the given schedule. That is, you have to assign a seat to a person when they arrive to work. People are not allowed to move in the middle of the shift. That's just a condition the company insists upon. That just gets too complicated and inefficient. Seats cannot be double occupied. That's an obvious structural constraint, right? You can't give 2 people the same place to sit, so you have to account for that. And then these key proximity constraints. Seats must be aggregated into what they call pods, which are groupings of seats. So that's one of the ways in which they imagine implementing this adjacency requirement. The solution. This problem, I'm sure many of you know this sort of what's called the quadratic assignment problem. This is pretty easy to see. This is fundamentally a quadratic assignment problem. Quadratic assignment problems are notoriously difficult. In fact, if you just try to, even though I made all these big claims about what you could solve with integer programming, the fact is, if you aren't at least a bit smart about decomposing this problem today, you won't be able to solve it. So the consultant had to invent a variation of the model in which what they do is they solve for a subset of the seats and then they fix them. Then they pick another subset of the seats and they solve for them and fix them. They do that sequentially. And the result is an algorithm that runs in about 3 hours. And one part I particularly like about this application is that the Gurobi solver was 3 times faster than any of the other solvers that I've tried. I won't tell you what the other solvers were. But it was all. So I was very happy about that. Total man hours to develop the solution for one person was 3 months. So that's pretty fast. And what was the ROI? The ROI is not dollars. The algorithm is run once per week. Human schedulers, when they were doing the scheduling, took a full day to develop a schedule rather than 3 hours. And the entire company, for this key function of running the call center, was dependent on a single person completing this task. So one person became all of a sudden very important for the company. And if that person left and you had to hire a new person, you had to train them. And different individuals had different levels of capability. Some of them could produce much better schedules than others. So you have this unevenness in the schedule. And with this solution, all of that disappeared. Not dependent on one person. You get a solution in 3 hours. It had much better quality. Actually, the employees really liked it. It made much more sense to them, the solutions. And anybody can run it. It was easy to deploy and run. And the solution, you could just take the solution as it came out of the solver. No management fiddling around with the solution was necessary. You could just use it as is. And in addition, what often happens with these applications is after they're in place, you discover other uses for them. And in this case, this turned out to be an important planning tool for this company to use to properly time when they would expand the call center as the company grew. and felt they had much better control over that aspect of their business. Right? And again, the technology was critical. So I think I've run out of time. This is my second case. I'm going to have to skip the only logistics case that I had. I apologize for that. And I thank you for your time. Thank you. And take this.
Thank you very much, Dr. Robert Bixby. Very interesting historical review and very interesting actual problems. Okay, next presenter is Dr. Fowler. Professor Robert Fowler is an authority on the design and implementation of computer software to support large-scale optimization. He's a principal contributor to the creation of AMPL, a widely used modeling language and system for formulating and analyzing optimization problems. His related activities include authorship of a popular book on AMPL and the founding of the company AMPL Optimization. He has also been a key contributor to the NEOS server project and other efforts to make optimization services available over the internet, and has supported development of open source software for operations research through his service on the board of the COIN-OR formulation. Professor Fowler is a recipient of the Informs Fellow Award and the Guggenheim Fellowship. He is a member of teams that received the Informs Computing Society Award for AMPL and the Mathematical Programming Society's Bill Orchard Hyde Prize for NEOS. He holds a BS in Mathematics from Massachusetts Institute of Technology and a PhD in Operations Research from Stanford University. And since 1979, has been a member of the faculty in Industrial Engineering and Management Science at Northwestern University. Okay, please start your presentation.
Okay. Hope you can hear me. So this talk is intended to be complementary to the talk that Dr. Bixby gave by talking about the software that helps you use these wonderful improvements in the algorithms and make them available. And it centers on this idea of a modeling language for optimization. And what I'll do is first say some things in general about modeling languages, and after a certain amount of general talk, you begin to wish to see some examples. So I'll give an introductory example that actually shows what I'm talking about. And then I will spend much of the remaining time talking about people who use these, who it is that actually uses these kinds of tools. And, whoops. Should be. It's back. It's okay. I'm pointing it later. And at the end I'll say a bit about where this idea may go in the future. And so here I'll talk about some more complicated studies. And so sort of behind the whole idea of modeling languages is that if you want to make optimization work as an application, there's a certain cycle of activities that you perform. You start out, you have to communicate with the person who has the problem, and you have to build some sort of mathematical model of optimizing what they have in mind to improve. And you have to build some sets of data to test it on. And then from those you generate some problems that you can solve. And then you feed the problems to these wonderful solvers that are going to find solutions quickly. You solve them, and now you look at the results. Now, if only that were the whole thing, it would be very easy. But unfortunately, at that point, you have to start over again. Because you look at these results, and if you're building a model, what you see is that the results are never when you start out what you wanted. You go back to your problem owner and they say, well, there are some things about your solution that aren't right,